Hello and welcome to the Chemistry Academy. In this video we're going to go over National 5 nuclear half-life calculations and also the uses of radioactive isotopes. If you're looking for help on the types of nuclear decay that we look at in National 5 Chemistry, I will link my video containing that below, or you can head to my National 5 Chemistry playlist and find my nuclear radioactivity video. To get started with the half-life, we need to know the definition of what half-life is. And this is a definition you probably want to know word for word, just in case you do get asked it in your exam. So the half-life of a radioactive isotope, so a substance that is radioactive, is the time it takes for the radioactivity of that substance or isotope to decrease by 1/2 or 50%. So if we have a look at this graph here, this is a graph that shows us the decay, the nuclear decay of carbon-14. Now, we from this graph can determine what the half-life of carbon-14 is, because down the y-axis we have percentage of carbon-14 atoms remaining, and then along the bottom we have time, how old the sample is in years. If we're looking for the half-life, then we're looking for the amount of time it takes for it to decrease by 50%. So if we start at 100%, we want to know how long does it take to get down to 50%. From looking at the graph, we can see that that takes 5,000 years, because if we look down the y-axis for where the line is at 50%, that corresponds to a time of 5,000 years. If we look at this next graph here, this graph's a little bit different because down the y-axis it doesn't have percentage, it has counts per minute, but that's essentially a measure of radioactivity. We know that the half-life is how long it takes for the radioactivity of a substance to decrease by 1/2 or 50%. So if the count rate starts at 80 counts per minute, we want to know how long does that take to half. Half of 80 would be 40, so we look down to see where the line is at when you're at 40 counts per minute, and we can see that corresponds to 2 days. So it takes 2 days from it to fall from 80 counts per minute to 40 counts per minute, which means the half-life is 2 days. We can confirm that from this graph by then looking at how long it takes to decrease by 1/2 again. So from 40, half of that would be 20. To go from 40 counts per minute to 20 counts per minute, that is taking from 2 to 4 days. So again, that's another 2 days. So we can see that the half-life is consistently 2 days. Every 2 days, the radioactivity of that substance will decrease by 50% or 1/2. One thing to remember about the half-life and radioactive decay is it is a spontaneous process that is not affected by temperature, pressure, or the amount of substance you have, anything like that. It is just a fixed rate, so nothing will change it except for having a different radioactive isotope. So each radioactive isotope has its own half-life, and that does not change regardless of the conditions that the radioisotope is in. So let's go and have a look at some half-life calculations, because these are the most common things you'll get asked to do in your chemistry exam. So we get a couple of different types of half-life calculations when it comes to the chemistry exams. We're going to look at the 3 main different types that we get, just so you have a strategy and a process for answering all of them. So the first one here is telling us that the half-life of bismuth-210 is 5 days. And then it's asking what mass would remain after 10 days from an original sample of 80 grams. So important things to jot down would be what is the half-life. So we can see from the question that the half-life is 5 days. So then we would note down T1/2, which is just shorthand for half-life, is 5 days. Okay. We then have the mass of the sample, starting at 80 grams. And then we're wanting to find out how much you would have left after 10 days. So that would be time passed. So the main thing that you're all usually trying to start off working out in these half-life calculations is how many half-lives have actually occurred in the amount of time that has passed. Or there's usually some way that you can work out how many half-lives have happened, even if it's to do with what sample mass you started with versus what you've ended up with. Okay, so you're usually always trying to start off by working out how many half-lives have taken place. So we know how much time has passed and we know what the half-life is, so that means we can work out how many half-lives have happened by dividing the time that's passed by the half-life. So the time passed over the half-life would be 10 over 5, which means that we have undergone 2 half-lives. So that means we need to take our 80 grams of sample and half it consecutively twice. Now the halving consecutively bit is important. You have to half it in 2 stages. Otherwise, you won't end up with the correct mass. So we take the 80 grams and half it once, so that would give us 40. And then we half it again, which then gives us 20 grams. So that's how much we would be left with. Now, when you're wanting to double check that you've done the right number of half-lives, the best thing to do is count up the arrows that you have drawn. So the first arrow represents the first half-life, the second arrow represents the second half-life. Okay, so that will be our final answer for this one. There will be 20 grams of the bismuth 210 left by the time 10 days has passed. If we then look at this next question, which is slightly different, we've got carbon-14 has a half-life of 5,600 years. An analysis of charcoal from a wood fire shows that its carbon-14 content is 25% of that in living wood. How many years have passed since the wood for the fire was cut? So in this question, again, we've been given the half-life, so we'll note down T a half equals 5,600 years. We're then told that the final mass that's left, or percentage of the sample that's left, is 25%. And we can assume that we start off with 1,000%, so we can put the initial 100%. So how do we find out the number of half-lives in this instance? Because remember, that's where we usually always want to start. So we don't have the amount of time that's passed this time, that's what we're trying to work out, but we do have what's left of the sample. So we can work out how many times has the sample consecutively halved in order to get to 25%. So if it underwent the 1 half-life, it would have gone down to 50%. And then after another half-life, that would take it to the 25%. So again, if we count our arrows, we can see that it's undergone 2 half-lives. That then means that we can work out how much time has passed because we know what 1 half-life is. So then to work out what 2 half-lives would be, we just times it by 2. So 2 half-lives is 2 times the 5,600, so that would give us 11,200. So that would give us the answer C. So you can see how it's kind of the same but a little bit different. You're still starting off by working out how many half-lives have taken place, but this time we've used it by what's left of the sample as opposed to how much time has passed. So then last question here, we're looking at the radioactivity of an isotope is found to be 1/8 of its original value after 27 days. What is the half-life value for this radioisotope? So in this instance, we're trying to calculate the half-life, but again, we still want to start off with working out how many half-lives have taken place. So we know that the final amount that we have is 1/8 of what was left. So sometimes they'll give percentages, sometimes they'll give fractions, sometimes they'll give masses, but it's all the same. If you're asked what percentage of the sample will be left, then you start off with a percentage, so 100%. If you're asked what fraction will be left, you start off with a whole, so that would just be 1. And if you're asked what mass would be left, then you start off with the initial mass that you're given. So that's how that kind of works for the different questions. So we've got the final mass to be 1/8, the time passed is 27 days, and then we're trying to work out what the half-life is. If we're working in fractions, it means our initial proportion or fraction of the substance will just be a whole, just 1. So we need to work out how many half-lives we need to go through to get to 1/8. So if we take the whole and half it once, that gives us a half. If we take it and half it again, then that gives us a quarter. And then halving that again gives us the 1/8. So this time we've got 3 arrows, which means that we've undergone 3 half-lives. So this time we know that there's been 3 half-lives. We know those 3 half-lives have taken 27 days because 27 days have passed. So 3 half-lives are 27 days long. So then 1 half-life would just be the 27 divided by 3. And that would give us 9 days. Okay, so again, we've started off the calculation by working out how many half-lives have actually taken place, and then used that information to then work out how long 1 half-life is, having been told how much time has actually passed. Okay, so that's the sort of 3 different types of questions you will get asked in terms of the half-life calculations: working out how much of a sample is left, working out how long a duration of time has passed, and then the third example was then calculating what the half-life of the isotope actually is. So now we'll go back to the big whiteboard and look at the uses of radioactive isotopes. So finishing off with uses of radioactive isotopes, there are a couple of things we need to consider when deciding what radioactive isotope we're going to use within a given context. And those 2 things that we need to consider are how long is the half-life of that radioactive isotope, and what type of decay, nuclear decay, does it give out. So in your exams you will come across different contexts of the uses of radioactive isotopes. So this is just a general help. Sometimes it is common sense, but just to get your head around it. So if we're looking at it in a medical application context, so like radiotherapy for cancer patients, or if you're going in for like a radioactive scan so they can see if you've got blockages anywhere in your digestive system, things like that, we always want the radioactive isotope to have a short half-life, because radioactivity, as we know, is damaging for our cells and our DNA, so we don't want to be exposing the insides of our body to radioactivity for longer than we have to. So the short half-life means that the patient won't be exposed to excessive amounts of radiation. And we also need it to penetrate through the skin, because normally there is a reason that we're trying to get the radioactivity in the body. We either need it to come out to be detected in the case of a scan, or if it's in the case of radiotherapy to treat cancer, we want it to penetrate into the skin in order to destroy the cancer cells. So that's the things that we normally want when we're using the radioactive isotopes in a medical context: a short half-life so that the patient's not exposed to prolonged bouts of radioactivity, and that it can penetrate through the skin, so either the radioactivity can be detected or it can get into the body to actually destroy any cells we're trying to destroy. In day-to-day context, so those sorts of contexts you will come across will be like in fire alarms, things like that, usually some form of safety. Normally we then want the half-life to be quite long, because we're not wanting to replace our fire alarms all the time. If we forget to replace them, then it means we're potentially going to end up with the house going on fire, not knowing, so it's dangerous. So a longer half-life in these everyday contexts is better. But then we also need it to be non-penetrating, so we need it to be alpha radiation, so that it's not going to be penetrating our skin and getting into our body and harming our cells. So if it is something day-to-day that's outside of our body, we do want the type of radioactivity to usually be alpha decay, so that it's not penetrating. Sometimes beta's fine if it's in a far enough away, or if there's like a metal shield around the radioactive source or something. But that's usually what we're looking for in the day-to-day type context that you'll come across. I did mention in my types of nuclear decay video that radiographers who work in the hospitals doing x-rays and these sorts of scans that use radioactivity all the time, they wear lead vests in order to protect their vital organs from any excessive radioactivity. They will also leave the room when they actually perform the scan, so again, not exposing themselves to excessive amounts of radioactivity. And they're also, if you as a patient or someone who needs a lot of x-rays and scans, they do monitor how many of these you're getting and how frequent, because again, we don't want to be exposing ourselves to excessive amounts of radioactivity, because it's not good for us. Okay, so that's our whistle-stop tour of half-life calculations and uses of radioactive isotopes. So I hope you found this video helpful. If you did, please give it a like. Don't forget to subscribe, and I'll see you again soon.